Good evening, ladies and gentlemen. Ramadan Mubarak to you all, and may the first day of the month bring you blessings. Welcome to the webinar on current trends in the application of green nanomaterials in enhanced oil recovery. I am Rabun Redar, the chairman of the SPE Erbil Section, and it is an honor to be moderating this session alongside Mr. Didar, the award and recognition chairperson at SPE Erbil Section. Our distinguished speaker today is Dr. Jagar, whose extensive expertise in nanochemical EOR makes him a leading authority in this field. Dr. Jagar holds a PhD from Soran University, a master's degree in petroleum engineering from Heriot-Watt University, and a baccalaureate in petroleum engineering from Korea University. With over 60 scientific articles on various topics in the oil and gas industry, currently serving as an associate professor at Palacky University in Olomouc, and a lecturer at Soran University. His commitment to education and research is commendable. Prior to his academic career, Dr. Zagar gained practical experience as a field engineer at Nasser Service Company, further enhancing his understanding of industry operations. He has also served in leadership roles, including chairperson of the SPE Erbil Section, our former chairperson, demonstrating his dedication to professional development and knowledge sharing within the community. So before we proceed, I would like to remind all participants, in order to receive participation certificates, kindly ensure you fill out the form that will be shared with you at the end of the webinar. Your cooperation in this matter is greatly appreciated. So without any more waiting, I would like to hand over the floor to Dr. Zagar. The mic is yours, Doctor.
Yeah, good evening, everyone. At the beginning, I would like to thank the team of Erbil Section of SPE and Kurdish Petroleum team for arranging this webinar. So as Rabun mentioned that I would be talking about current trends in the application of nanomaterial, most focusly with the nanocomposite and green materials, green substances in enhanced oil recovery. So before I start, I would like to share with you my research record based on the Scopus and Web of Science, like web metric. So currently I have more than 50 articles which are published and recognized by Scopus, with around 48 publications recorded in the Web of Science collaborative. The research area that I'm focusing on is mostly, as shown here, reported by Scopus. I'm focusing on the energy, 50% of it, and chemical engineering, chemistry, and material sciences. And I have lots of peer review and review service for international journals, as shown here. The journals which are related to the energy, to the petroleum engineering, and material sciences and its application, and I was serving.
Sorry for interrupting, but the slides aren't changing. Can you check, please? It's still on the yeah, now changing. Yeah, yes, please go ahead.
Yeah, I was showing this slide about the research record, and I explain it. So about my research study area, the number of publications, citation that I have, and the review service. So mostly I'm doing peer review for some high impact factor journal, and I was serving as editor and continued with these two journals, like Journal of Frontiers in Chemistry and Journal of Petroleum Exploration and Development with impact factor 7.8. And since 2013, I am a member in Society of Petroleum Engineers, SPE. I served for 3 years as faculty advisor and then the chairman of the Erbil section. And currently we have a good project about development of shell inhibitor for one famous problematic formation in the Kurdistan region, which is called Kolosh Formation. We had a fund and grant from Petroleum Processor Company. So till now we have good result, but it's a matter of time they will be published as well in some good journals. So the content of today's lecture will be about some introduction with the regard of the study area, then some description about nanomaterials and how we prepare green nanomaterials. Then we have two most important parameters inside the reservoir, which are interfacial tension and wettability, and the effect of these nanomaterials on these two mechanisms and parameters of the reservoir, and then wear recovery, which is the most important goal of our studies. And this, for your information, this presentation is outcome of our publications, about 9 publications that we did about impact of nanoparticles in improving well recovery. So this is just an outcome of the studies that we did. So the main goal.
We lost your presentation. Can you please start again the presentation?
Okay.
Yes.
So the main goal in our research work is to improve oil recovery factor. So what we did for improving oil recovery factor, we prepared some different green nano composites and nanomaterials. So then we confirmed the validity of the nanomaterials which are prepared by ourselves in the laboratory in a green way. This is the most important thing. So we want to make the methods of improving oil recovery to be environmentally friendly. So that's why we try to use some green-based nanomaterials or green substances. So how it can be achieved? By altering the wettability and by reducing the IFT and interfacial tension in the porous media. You know, the wettability and IFT exist inside the porous media, which is the outcome of the interaction between the different phases of fluid that we have with the rock that we have inside the porous media. So as it's clear, like we have carbonate reservoir. So we mostly focus on carbonate reservoir because the state of the oil inside the reservoir is oil wet. So when the oil wet system is there, it's difficult to extract hydrocarbon easily. So that's why we focus on the carbonate reservoir, and we have different methods usually as shown here. We have primary, secondary, and tertiary recovery mechanisms. Usually we try to start the production with primary, and then we should implement some other methods in order to improve or extract hydrocarbon from the reservoir. So usually what we do, we try to distract the interaction between the fluid and solid inside the porous media in order to make it free to be produced by balancing these forces that we have here: viscous force, gravitational force, and capillary forces. So water flooding is just to maintain the pressure, and then water flooding, when we do it, it will leave high amount of hydrocarbon and sweat inside the porous media. Then we should focus on chemical EOR. So nanofluid flooding is one of the techniques that nowadays is considered by researchers and by some companies. So in our project that I'm presenting here, usually we focus on combining surfactant with nanoparticles and water as distilled water, and water at different salinity levels and different composition as smart water. So usually when we discover reservoir, we have hydrocarbon, we have a state like this. When porous media is full of crude oil, for sure we have connect water. And then when we do the production by water flooding, what will happen? We will have a bearing of water, and then large volume of hydrocarbon, large amount of hydrocarbon, which is left and swept inside the porous media. And then by chemical EOR or by chemical flooding, we can extract more hydrocarbon, definitely, but still high amount of hydrocarbon is there. So we believe that nanofluid flooding can increase the oil recovery and change the even penetrate the channels, the pore spaces that we have inside the porous media in order to increase the production through the mechanisms that I discussed earlier. So recovery efficiency, recovery factor mainly is dependent on the microscopic displacement and microscopic displacement. Within the macroscopic displacement, we have reservoir heterogeneity, we have well pattern, we have log matrix, and we have mobility ratio. So with our studies, we try to control our balance mobility ratio. So now when we have a mobility ratio higher than 1, usually we have interfingering. And we try to reduce it to less than 1 in order to have even flow, to have better sweep efficiency, and to increase production. On the other side, we have 4 main factors which are influencing the microscopic displacement inside the porous media as shown here. The first one is interfacial tension, the second one is workability, then capillary pressure, and then projective permeability. With having nanofluid injection, the main target is to alter all these factors, including IFT, wettability, and even capillary and projective permeability, with some mechanisms as shown here. So recently, like we have a publication which is published by Zheng et al. About surface modified silica nanoparticles in 2024. They enable to increase or additional like 20% of original oil per in original oil in place. So this is good. They reported that they did this, they obtained this improvement in the recovery factor through shifting the relative permeability. And then another research work was published by Liu et al. In Fuel in 2024 about Fe3O4 silica oxide. They prepared this nanomaterial from biological sources, from some bacteria, and it is reported as a green-based nanomaterial. And with injecting a nanofluid with 500, only 500 ppm part per million, they increased oil recovery by 15.56%. This is a good achievement. And then in Journal of Cleaner Production, it is one of the good journals, Mehran et al. Reported some green nanomaterials, which is silica-based, and they used only 0.4% weight percent of nanoparticle mixed with water, and they improved oil recovery by 22.6%, which is good outcome. And more recently, in 2023, a group of researchers, they published an article about reviewing the application of green nanocomposite in UVA. And all of our research and publications that published earlier to this day, they cited and they reported in their article review. In terms of the field side, there are some field applications around the world. The first one in Ghawar oil field in Saudi Arabia, they used like nanoparticles. They did nanoflooding of 255 barrels by mixing 5 kilograms of carbon nanoparticles in the water, and they increased oil recovery up to 86%, which is a good outcome. And then in Castelia and Chichimini oil field, which is located in Colombia, they also pumped they pumped 200 barrels and 150 barrels of nanofluid into different fields Castelia anti-chimney, and the performance was good, which is around 11% of original oil recovery. And then one application of the nano in Aigalo oil field, which is located in Hungary. They also injected 400 cubic meter of silica-based nanofluid. They mixed 1 gram of silica with 1 liter of water. They increased oil recovery up to 50% and reduced the water cut to 40%. And I would like to focus on this field application that they did in Hungary. This is the location of the field, which is located in Hungary. And then this is the surface facility that they used in order to inject the nanofluid. Schellenberg service company was responsible to implement that. And this is the data that they reported for 2 years of production. As can be seen here, the oil production is highly increased, and the water cut from above 90% is reduced to average 40%. And this is also reported as a good outcome from the nanofluid flooding. Usually when we design the experimental work for our papers and our work, you should firstly prepare the nanomaterials that you want to use, or you just do the characterization for the nanomaterial that you are going to implement. And then we have some methods for preparing nanofluid. You should prepare it well, and you should focus on the stability of the nanofluid. And then we have some application of IFT, contact angle, and core flooding. So for contact angle, before you do the experiment, firstly, you should prepare the thin sections from the core samples. So you should cut the core plugs into different thin sections, and then you should age them. Like usually age these samples for like period of 2 to 4 weeks in order to represent reservoir condition, which is oil weight. And then we have this set up in order to do the measurements of contact angle. And then for core flooding, same, you should prepare your core plugs. The core plugs should be prepared in good way. You should clean them, smooth the surface, and then measure the porosity, permeability, and then you should age them. So usually you can use 2 weeks to 4 weeks in order to age the core samples and to return them back to the reservoir condition, which is oil wet state. So then we have this setup. Usually we control the temperature and pressure in order to do the core flooding and oil displacement through the prepared core sample. So for green synthesis of nanocomposite, we have different methods in order to prepare nanomaterials. And nanomaterials are these small particles with the size ranged like around like from 1 to 100 nanometers. Then they can be assigned as nanoparticles or nanomaterials. For nanomaterials, we have different types. Nanoparticle, for example, nanocomposite, then we have nanotube, nanosheet, we have different types. So we choose to use green nanoparticles in order to be environmentally friendly, and we use green method. That means we are using some natural resources, that contains the enzyme and protein with the ability to have catalyze the reduction of the metal ions. With reduction of the metal ions, then we can form nanoparticles. Usually in our studies, we use plant extract, which can be the leaf, root, or seeds of the plant. But microbial, such as bacteria, fungi, and algae, they also used by some other researchers, and they are considered to be natural sources to prepare nanomaterials. Within this method, not only the plant source or the natural source, the source that we use for the preparation of the nanoparticles is important, but the solvent, the chemical reaction, and the device that we use also important. They should be environmentally friendly. During the reaction, during the experimental work, we should focus on that to not consume a lot of energy. We should focus on that to don't due to high or harsh conditions of the reaction. So that's why we should be always careful for the solvent to use water or ethanol for the techniques, synthesis technique, ball milling, we use ultrasonication and grinding. And we have some factors which are important to usually take into our consideration when we select the plant source. For example, reaction potentiality, stabilization ability, availability of the plant source. It should be something which is sustainable and renewable. And then chemical composition is also important in order to be able to form nanoparticles, and then the pH and temperature stability is also important, because during the reaction, during the experiment, we might change the pH and the temperature. But pH, for example, when it is above 11, it will give you nanoparticles, but when it is less than 5, it will give you maybe nanotubes. So you should be very careful about the stability of pH and temperature. These are some plants that we used in our work, and here we have the procedural steps that we consider to prepare ZNO-SiO2 xanthan from the pomegranate seed extract. And then the below one is the bottom one is the procedure that we consider for preparation of Fe3O4 mineral soil nanocomposite from the Eudia hortensis leaves. So what's important here? The phase that you prepare the extract, and then the salt that you use to be mixed with the extract, and then the reaction. You should keep the pH, for example, in a certain level, and then check the temperature of the solution in order to have a precipitate, and then you should burn it in a good way in order to obtain nanoparticles. And then refluxing is also, and grinding is important when we want to mix the nanoparticle with some other natural polymer in order to have green nanocomposite. So from here, we can see the methods that we always consider for characterization of the prepared nanocomposite. Usually we do X-ray diffraction. From X-ray diffraction, we can have the crystallinity of the material that we use, the chemical composition of them. This one just to confirm if our method, if our result is fine, if our result is okay with the standards that we have. We have one international database of diffraction for all materials. Usually what we do, the peaks that we obtain, the patterns that we obtain here, they should be compared with the database that we have internationally, and then you can compare the validity of the nanocomposite that you have and nanomaterials that you have. These are the 8 patterns of the XRD for 8 nanocomposites that I considered in this presentation. And then we have FTIR. Also, we use this technique in order to estimate the functionality of the nanocomposite that we have. For example, here we have 8 spectrums of FTIR for 8 nanocomposite that we prepare. So here also we have a correlation table of different functional groups. For example, phenolic. For example, we have alkaline, acidic, base functional groups. So with having these spectrums and comparing with the correlation tables that we have internationally, based on the standards, you can compare the fabrication of the nanocomposite that we have. And more importantly, we have scanning electron microscopy, which is SEM. SEM is good, which confirms the size of the materials that we prepared and also the morphology of the material. For example, here we have 6 different samples of SEM, like images of 6 nanocomposites that we presented here. So as can be seen, the range of the particle, the size of the particle is within the nanometer range. So that's how we can confirm the accuracy of the work. So sometimes you will prepare the nanomaterial, but when you do this characterization, maybe it's not confirmed. So then you need to repeat the work and change your plan. So what I am presenting here is the outcome of many trials and many trials of preparing the nanoparticles, and this one is the final one, which is the confirmed one based on the characterization that I presented here. So after confirming the fabrication of your material, then you should prepare nanoflow. So for this project that I'm presenting here, we use different types of aqueous phase of the fluid. For example, surfactant, mutual solvent, loose water, smart water, distilled water, and formation water, in order to check the effectiveness, the performance of the nanocomposite with different types of the solution in order to obtain the best one. Even the surfactant that we used here, it is the natural surfactant from cyclamen persicant plant. So, and the mutual solvent is ethanol and methyl alkyl ketone, and we changed and built the smart water solution from using these different salts. This is the method and the procedure that we use usually to prepare the nanoparticles. We can mix them using sonication, and then we should be careful about the stability of the nanocomposite, and we have, for example, sonication in order to have to mix the nanoparticles well, to be sure that we have good dispersion during time. So usually we use different concentrations of 500, 1000, 1500, and 2000 ppm of the nanoparticles. And when we do prepare the solution, the nanoflow solution, we do some tests and measurements for the density, conductivity, pH, and viscosity. So these are some examples of the nanoflows that we prepared. For example, here we have the combination of TiO2 quartz, ZnOSiO2 xanthan, ZnOSiO2 bentonite with different water types, like different levels of salinity, like distilled water, low salt water, moderate salinity water, and high salinity water. And from this table, you can see the combination of TiO2 SiO2 polyacrylamide nanocomposite with smart water solutions. We have different smart water solutions here. And then nanocomposite with natural surfactant. Firstly, we should obtain the CMC of natural surfactant, and then we mix the nanocomposite with a different concentration with the optimum concentration of surfactant, and then we check the performance of the hybrid chemical EOR method. And here we have the dispersion of nanocomposite with the mutual solvent. So we have this protocol when we prepare the nanoflows and some measurements in order to identify or characterize the nanoflow. Usually for nanoparticles, you should do characterization. For nanoflows, you also do characterization, and then we apply it for AOR. These are some pictures of the nanoflows, different nanoflows. For example, this one is the dispersion of TiO2 quartz with different salinity levels of water. And by leaving these nanoflows for 3 days, we still can see a good dispersion stability. Dispersion stability is very important because when we inject the nanoflow inside the porous media, nanoparticles should remain stable inside, dispersed inside the water. And if they are not dispersed, so it means they will be not effective and they will be lost inside the porous media. So, and this one is another example, as you can see at day number 5, day number 4, for the nanofloat with less concentration, nanoparticles are trying to precipitate. And then at day number 6, what happens? Nanoparticles are precipitated at the bottom of the vessels. This is important to be known in order to check the injection of nanofluid and flow of the nanofluid inside the porous media. From here, I would like to talk about interfacial tension reduction. Interfacial tension, it's a force that usually happens when two immiscible fluids exist. We have this condition inside the porous media, so interfacial tension is very effective, which attracts hydrocarbon and make it immobile. So it has been believed that nanomaterials can create a layer, as shown here, a thin layer. This layer, because nanoparticles are attracted to the interface that you have between two immiscible fluids, this layer will try to make hydrocarbon to be free and separated from the water, and then they can be movable easily. So it is reported that the IFT between oil and brine inside the porous media is usually between 20 to 34 millinewton per liter. And then according to Schenk, 2014, when we try to reduce the IFT from the initial value inside the reservoir to 10, then we can increase oil recovery by 5%. And if we reduce it to ultra low values, then we can increase the oil recovery up to 20%. So IFT is one of the dominant mechanism of UR which influence and affects the recovery of hydrocarbon inside the porous media. These are some results of our research. For example, here we have ZnO-SiO2 xanthan nanocomposite, which is mixed with water at different salinity level, as shown here, and at different temperature and pressure condition. So as can be seen, we have the best performance when the nanocomposite is mixed with low salinity water. And the good thing is that this nanocomposite is mostly effective when we have a high temperature and high pressure condition. And from the other side, we can see different images of the crude oil droplet with the presence of TiO2 quartz nanofluid. So they have different ranges and different values. That's what we do. Usually we take this picture, the image, we screenshot it, and then we analyze it with using some software and tools by computer, and then we can identify the IFT value. For wettability alteration, wettability is the tendency of the fluid to spread or adhere to a solid surface in the presence of other immiscible fluid. So we have this situation inside the porous media. We have rock surface, we have crude oil, and we have water, which are immiscible. They cannot be mixed. So when you have oil wet, the problem is that after like injection of water or having water influx, what happens? High amount of crude oil would remain inside the porous media. So usually when we have oil wet system, it means the contact angle between the oil droplet to the surface of the rock is higher than 90 degrees. And then we try to reduce it by injecting nanofluids to be less than 90 degrees. So this is how it happens. When nanoparticles are injected inside the porous media, they will try together to arrange themselves at the interface between the oil droplet and the solid surface. they create a wedge film which can create higher disjoining forces, and it will make hydrocarbon be free and be moved towards the production well to be produced. This is how it works inside the porous media. So for contact angle, the minimum contact angle that was achieved in this project was 19 degrees, which is very low. When you have 19 degrees, it means the rock and the porous media is strongly water wet. So with having a strong water wet system, it means oil is free to be moved and it can be easily produced. So this was achieved when nanocomposite number 6, which is ZNO, not monolinite, was mixed with 5,000 ppm of natural surfactant. Okay, so the initial contact angle was reported to be 134 degrees, and then by injecting surfactant, it was reduced to 51.5. When the nanofluid without surfactant with water was injected, it's reduced to 30 degrees. But when we mixed the nanoparticles with the surfactant, what happened? It was reduced to 19 degrees. That means the nanocomposite that we use is increasing the efficiency and performance of the surfactant as a conventional chemical EOR method. These are some screenshots of the crude oil droplets on the surface of the rock. So, for example, here we have the contact angle is higher than 100. It's 109, sorry. We can see it here. So it's obvious that crude oil is highly attracted by the rock and it's immovable. So, but the upper one and the contact angle is less than 90, and this for this condition is about 48 degrees. It means, and it's obvious, the oil is almost free to be moved. So usually, like we reported this mechanism as the wettability alteration under the influence of the nanofluid. So as can be seen, when we have an oil bank, it is almost oil well, and oil is attached to the rock as a residual oil, as a trapped oil, so it cannot be moved. Then when nanofluid tries to penetrate this zone, and we have like transition zone between the nanofluid and oil bank, so like contact angle will try to be changed and reduced till it is completely become nanofluid bank, and then what will happen? Contact angle will be reduced highly to strongly water wet, and then hydrocarbon will be free to be moved. So the most important part is oil recovery. So according to the EIA report, and ExxonMobil just published an article maybe 3 to 4 weeks ago. They reported that the global will be needing, like the world will be needing energy, and they would be needing crude oil, gas, and natural resources for a long time. So till 2050, we will need the same amount of natural resource that we have, and it will be increased. So that's why fossil fuels still remain demanded by the world for the energy. So discovering new oil field is difficult and it's costly, and most of the good oil fields around the world, they already discovered and they are developed. So usually companies and researchers are trying to expand the life of the current producing oil fields, and this can be done by EOR when the target is increasing or producing extra 20 to 30% of original oil in place. So nanotechnology is one of the main concern in order to be used, or main technology to be used in order to achieve that goal. So in this project, we did 26 tests of core flooding. So we used like different types of core plugs. 25 of them were carbonate and one of them sandstone. So the average pore volume of the core plugs that we prepared is about 9 cubic centimeter, and the permeability is varied between 3.2 to 30 millidarcy, and the porosity between 7 to 18.4. So the injection rate of displacement of well displacement is varied from 0.1 to 0.6 cubic centimeter per minute, and the pressure was ranged between 1,400 to 2,000 psi, and the temperature is varied between 50 to 75 degrees Celsius. So the outcome of core floodings from all used nanocomposite is presented here. So the maximum oil recovery factor that was obtained is about 21.41, and the minimum one is about 5.3. So for the first nanocomposite, when we mixed the ZnOSiO2 xanthan with low salt water, we were able to obtain 19.28%, and this is the profile of the oil recovery and the pressure drawdown during the experiment. And for the second nanocomposite, when we mixed the TiO2 SiO2 pump with different smart waters, we didn't get the good outcome from it, and the maximum recovery factor was about 10.5. It can be stated that nanocomposite was not effective with smart waters. And this is one example of the profile of the oil recovery and pressure during the oil displacement. So then we have the third one, when we used TiO2 quarters with distilled water, with mixing only 1000 ppm of the nanomaterial. So with distilled water, it showed the price performance, which is around 21%. And this is the profile of the oil recovery for different oil displacement or core floodings. So here we have when nanocomposite number 4 is mixed with low salt water, and it was injected into carbonate and sandstone rock, both of them. With sandstone rock, it was more effective, and the recovery factor was around 15.79. So, and then we have nanocomposite number 5, which is the NOSiO2 bentonite. We use it at 2000 ppm concentration and mix it with distilled water and low salt water. With distilled water, it showed the best performance, which is around 21.41% of oil recovery. This is the profile of the oil displacement methods, test for distilled water and for low salt water. With distilled water, it was around 65.41%. And the last one, when we disperse the ZnO montmorillonite with natural surfactant, as can be seen here, with the surfactant, natural surfactant, we were able to produce 8.2, and then with nanofloat only 6%, and like with a hybrid system of nanosurfactant, it was around 13%. Even the recovery factor is low, but we obtained a good result in terms of having a good performance and effect from the nanoparticles on the performance of the surfactant. So from this slide, we have the relative permeability shifting. Usually, as can be seen here, we use the experimental data that obtained from the core flooding and use a software which is called CIDR software. It's working based on the JBN. JBN is the famous, well-known method for measurement of the relative permeability. And based on the result that's shown here for different nanofloats, it confirms that the wettability alteration is there. And with having wettability alteration, we have different saturation level, and then it shows a good and nice shift of relative permeability of water and oil from the right side to the left side, and it lowers the residual oil saturation. The summary the summary of the work is presented here. Like, we have different publications as shown here for different nanocomposite with different conditions of the experiment. So here, from this column, from this row, it is about experimental conditions, the type of the nanomaterial, aqueous phase used, the salinity level, concentration, pressure, temperature, the formation type, permeability and porosity, and the performance evaluation, which is focusing on IFT reduction in percentage, contact angle decrease in percentage, wear recovery improvement in percentage as well. For the first work, which is published by Energy and Fuels and Journal of Molecular Liquid, we use ZnOSiO2 nanocomposite with water at Lusal level. So the ratio was about 1,350 and temperature 75 degrees. The type of the rock was carbonate with this range of porosity and permeability. The IFT reduction is very high, which is around 93%. Although the contact angle decrease is not too high, but it is water wet, it is below 90 degrees. That's why we have a recovery of nearly 20%. And for the second work, which was published by Fuel, it was the effect of TiO2 quartz with distilled water. Even we have a good performance in terms of IFT reduction, 90%, contact angle decrease, about 53%, and oil recovery, which is around 21%, which is good. And the third one is the effect of SiO2 montmorillonite xanthan with distilled water. The recovery factor was not good, and even the IFT reduction was not good, but the contact angle reduction was high, around 78%, but it was more effective with carbonate, with sandstone rock compared with the carbonate rock, which is around 16% of additional oil recovery. And the next one is the application of TiO2 SiO2 polyacrylamide with different smart water solutions. So for all of them, the outcome, the performance was weak, and the oil recovery, the maximum oil recovery factor was around 10.5%. And the next one, which is ZnOSiO2 nanoclay, which was also mixed with distilled water, and it gave the best performance. Even here, like, IFT reduction was high, contact angle was only about, the reduction of contact angle was about 50%, but the oil recovery factor was the highest one. So this nanocomposite with distilled water was effective with having good performance. When we mixed with natural surfactant, even the contact angle reduction or wettability alteration is very high, and IFT reduction is very high, but core flooding is not, oil recovery factor is not too high. So this needs more studies when we use the nanocomposite with natural surfactant. And the last one, like when we use SiO2 KCl xanthan with the mutual solvent of ethanol and MEK. So it was more effective with MEK, but still the performance is not too good. So it can be summarized that the nanocomposite that we use to prepare nanofloat, they are more effective with distilled water, they are more effective with loose water in terms of reducing the IFT, changing the wettability, and improving the recovery. But we noticed from our studies, when the IFT is highly changed, we have better oil recovery compared with the wettability alteration. So thank you very much for your attention, and if you have any question, we can have, based on the agenda of the webinar, we can have some QA time.
Thank you very much, Doctor. For all of those that are asking, there was just a little bit delay on the slide change. I will let the responsible officer know before uploading the saved recording. We might need your PowerPoint character and extract your voice from the current recording in order to sync them together and come up with a smoother and better recording for our archive and YouTube channel for those who missed some parts of the meeting or due to some delays. Okay. Thank you very much. Feel free to raise your hand or type your questions in the chat. We're here to address any questions you may have. Okay, Ms. Demon, yes, please go ahead.
Hello everyone, good evening, Ramadan Mubarak. Thank you, Doctor, for your insightful and informative presentation. I have two questions. First one is about pH. What's the impact of pH on nanoparticle synthesizing? I'm insinuating about the adjusting of pH. And another one is about dispersion stability, as you mentioned it. Can we control dispersion stability? If yeah, then how?
So about pH, yes, it affects. So it should be adjusted. For example, if you want to do to prepare nanoparticles, you should keep it like above 10. Okay, then you will have nanoparticle. So when you want to have nanotubes, there's another standards to do it. Like it can be lowered to, for example, unstable during the experiment. And when you do that, for example, you will use some salts, you will add it to the solution, and continuously you should monitor the pH limit, because if the pH is changed, that means the reaction condition will be changed, and then you will not get what you want. And secondly, for dispersion stability, so for dispersion stability, the good way that we use nanocomposite, usually the main idea is that to have polymer, some natural polymers combined with the nanoparticles, and these together will keep the dispersion in better way. So you should use something with nanoparticles, especially when we use metal nanoparticles. So if you use nanoparticles alone, you might have less duration of the dispersion stability. But when you add emulsifier or you use some surfactant or or polymer, so it will keep it for longer time.
Great, many thanks.
Liqa Idris, please go ahead.
Assalamu alaikum. Thank you for your this important lecture. And I have a couple of questions regarding the aggregation. If there's any, there's a possibility of aggregation during the application of nanofluids during the application of the nanocomposites as a nanofluids. And another question is regarding the costs. Is it like cost efficient? I mean, the preparation and the synthesis, even if it is like a green way or a green synthesis. So is it cost efficient or is it costly to prepare this nanocomposite? And thank you.
So for your first question about aggregation, yes, I was just answering Diman about that. And I showed some picture of the nanofluids that we prepared during time, for example, for 6 days. So when we prepare nanofluid, for example, you will use steering mixing. But after that, you should do sonication for like 2 hours, 6 hours maybe, in order to have good dispersion. And then when you have good dispersion, it will remain for a period of time. So usually we try to prevent the aggregation of the nanoparticles, and we obtain that, to be honest. So it's not a big deal here.
Can I interrupt you here? So sorry for interrupting you, but my question is regarding the application. So how can we maintain the nanotube fluid and prevent the aggregation during the application?
Inside the porous media, if it's about porous media, we cannot observe inside the porous media, but we did in the what we did inside, like in the laboratory. It was we just did some observation monitoring through some visuals, and it was obtained. The dispersion stability was obtained without aggregation for a limited period of time. And for your second question, like for example, if you have Kakravan, I just shared a slide which is about some calculation. Is it shared?
Yeah. Yes, we
Okay.
can see that.
I want to answer the question about from this example. For example, if you have a reservoir with this dimension, 500 meter in length and 100 meter in width and 10 meter in thickness, let's say we have the pore volume around 85,000 cubic meter. And then when doing tertiary recovery by nanoflow, it has been reported that we can have at least 20%. So with having 20% recovery, it means we have 70,000 cubic meter of production, which is equal to 107,000 barrels of crude oil multiplied by $88.5 million. But in terms of the nanofloat, if we have just a sludge of nanofloat to be injected, which is with this orange layer color, so it means it is about 5% of the total pore volume. So, and then if we use, based on the reported field application that I presented previously in my presentation, they used 1 gram per liter. It means we need 5 kilograms. And when we do the nano composite, it's nano with matrix. So it means one out of the third is nano. So it means we just need 1,650 grams of nanomaterials to be mixed with the water, and then to produce around like 100,000 barrels of crude oil from this reservoir and make the profit of $8 million. So it means it is effective, and that's why some companies are trying to do it. Even we have some examples here in our oil fields in Kurdistan. There are companies that are using nanoparticles for some applications with regards of the oil and gas industry. Yeah. Any other question?
Somebody's asking if we can send a PDF to them. Maybe I'll
This
check
one?
with the. Yes, maybe.
We will check. If I can, I will share it with you. Yeah.
Okay, yes. Any more questions, ladies and gentlemen? Yes, please go ahead.
So sorry, I'm asking many questions, but this
That's okay.
is very important. So regarding the size and shape and morphology of the nanocomposite after application as a nanofluid, have you characterized them after doing, post application?
No,
Have
no.
you characterize them to see the differences between before and after? In
No.
size, morphology.
No, until now, no, we didn't study the characterization of nanoparticle after the application. We just did it before application. But that can be done.
So that's
example,
give you maybe this kind of characterization, in my viewpoint, give you indication of the change before and after. In regarding the aggregation, because the different size maybe give you a very good indication about the aggregation. If it's, yeah,
we believe that like aggregation is not a big problem here. The absorption of the nanoparticles to the surface of the rock is main issue, because
you mean,
like, it makes
the size, it's not give you a good performance. In regard, like smaller nanoparticle give you good efficiency than the bigger nanoparticles. You mean the size?
Definitely we need the smaller size. So
So
that's
why
we
then
need to.
the aggregation is not a problem?
So I think it's not happening. What is happening here is
Okay.
the absorptions of the nanoparticle to the surface of the rock. This is what's happening
So-
usually inside the porous media.
So that's why the characterization after application is very important. So to indicate that there is no change in the size.
So yeah, it can be checked. It can be checked, but we have some other challenges which are maybe more important than characterization of the nanoparticles post application. We have this.
So
We have
thank you for
stability.
this.
We have
Yeah,
the effect of salinity. We have many other issues to be discussed,
yeah.
to be
There's many
studied and
factors. Yeah,
investigated. Yeah.
yeah. It's a very rich area, and there's very good topics for research. And thank you
Yeah.
for this topic. And I hope we can collaborate together in this kind of research. It's very important and it's very noble, actually. Thank you for your
You are
lecture.
welcome. If anything is needed, we can contact. Yeah, definitely.
I'll be delighted. Thank you.
You're welcome.
Thank you again, Dr. Jagar, for your enlightening presentation and engaging discussion. We really appreciate for taking the time to join us today and for delivering such an insightful webinar. Thank you to all the participants for joining us today. We hope you enjoyed our talk. Happy first day of Ramadan again. May this month be filled with blessings for you. Wishing you a peaceful and joyous night ahead. Ramadan Kareem and good night.